Welcome to this series of lectures. Here, this is a series on quantum computing. So, we'll first discuss um, in this episode that what is quantum computing and what are we going to do uh, basically in this course, a kind of introduction. So, nowadays we are hearing about quantum computers nearly every day in the news, in the popular media, like quantum computer will solve certain types of problems of it's of tremendous importance to mankind, problems that today are practically prohibitive or maybe even impossible to solve with current computers will be solved by quantum computers, like say drug discovery, gaining a better understanding of new materials like high temperature superconductors, new methods for machine learning, artificial intelligence, a whole lot of optimization problems, problems in financial services, in technology. So these things like quantum computers will even challenge and change the way we securely communicate information. So it certainly sounds like a really exciting future, but what exactly is a quantum computer and what it is really good for? And of course, when we will have one. So quantum computers, like quantum mechanics, it doesn't mean that they are just smaller, faster version of classical computers. In fact, uh, the quantum computers the speed that we get is a kind of byproduct. Okay, so nor are they another incremental step in the evolution of Moore's law. Okay, they are fundamentally different. They represent a new, fundamentally completely different uh, computing paradigm. You can say a paradigm that carries tremendous advantage for certain type of problems of importance. Now, in our known digital computer world, a bit is the basic element of information. The we can say rather the unit of information, which we know that it is a 0 or a 1. In quantum computer, we have quantum bit or qubit, which is a superposition of 0 and 1. So we are actually engineering and manipulating quantum mechanics. So quantum computing could really transform industries where there are significant optimization problems here. So we have got a lot of binary decisions, discrete decisions to make to figure out whether we should do this first or that first, whether we should do this kind of route or that kind of route, like that. Another way to understand the difference between a classical and a quantum computer is that if you look at, say, the quantum systems of quantum simulations, the quantum processor is a suitable tool for modeling other quantum systems, biomolecule systems. Okay. A lot of systems that we use, like material systems, work based on those quantum mechanical systems or quantum mechanical properties of those systems. Okay. We need a quantum machine in order to simulate quantum effects. We cannot have classical computers simulate quantum effects. When we can manipulate individual molecules and understand what is going on in these molecules, how they bond, what happens to their properties when they bond, what happens to the properties when they bond some different molecules. then we will be able to have a really good handle on generating new materials or novel materials that might be very useful. So this quantum computer have the potential to exceed the performance of the conventional computers for problems of importance to, of course, humankind, not only humankind, the entire Earth, inhabitants of Earth, businesses alike, in areas such as cybersecurity, material science, chemistry, pharmaceuticals, machine learning, optimization, and many other areas. Now we are just at the very beginning of quantum computing development, assembling and testing the first prototype processors. It is kind of being in the 50s at the at the very dawn of transistor-based computing. Then integrated circuits came. It led to the information processing revolution in the last century. So many people today believe that quantum computing will have a similar impact this century itself. Okay. Quantum computing and quantum algorithms present fundamentally new programming and algorithm design paradigms. We are still learning a lot about how to improve the individual components, lots of papers getting written every day. So in this series, our goal will be to understand quantum computing at an um, intuitive, a kind of foundation level. Okay, we begin the journey with a bit of history, like where from quantum computing emerged, especially with the sunset of Moore's law. Then we will investigate the core principles, practical application areas of quantum computing. Then we will delve into more math-heavy topics like quantum algorithms for cybersecurity, chemistry, optimization, financial modules, like all sorts of practical realities. We will look at different models of computation and how a quantum computer is different from a classical computer. We will talk about two of the foundations of quantum computing that make it powerful. And these two foundations, this is something that we need to remember very carefully. One is called the quantum parallelism, which will spend some good amount of time to understand what it is. Another is called the quantum interference. Okay, so these two things really enables the quantum computer to process information efficiently. Mapping the behavior of physical systems to computation. This is a real challenge. How quantum bits are realized with a wide variety of physical systems using atoms, photons, semiconductors, superconductors. Algorithms, they're different compared with what is possible on ordinary classical computers. They have new abilities allowed in quantum system. We will consider the business, science, and engineering implications of these advancements. Finally, we will run algorithms and business use cases on real quantum computers. Quantum computing is a very exciting field. There is a lot of promise to quantum computing, but there's also a lot of hype. We need to separate what's hype from what is reality. What will happen in the future versus what is happening right now.